So the seminar will be recorded, and you will receive the recording by email after the seminar is So once again, let me return to my presentation. So ATENA is about reinforced concrete modeling, and we model structural details, as well as nowadays engineers like to model the whole structures like the bridge, nuclear containment, or as you see here, the offshore wind power generation structures. Again, I would remind everyone who maybe joined us later to turn off the microphone so that we don't have any noises in the background. Okay, so something about our company. We are a small company located in Prague, Czech Republic. What you see is the picture of Prague. Unfortunately, this is not our office, yes. So this is the Prague Castle, one of the dominants in the Prague. And you can see it's blossoming. So this is a picture taken in the spring. Now we have summer. Also a very nice weather is right now here. So we are a small company, about 20 engineers, most of them with PhD degree. And we are very much active internationally in Germany, everywhere in Europe, in Asia, United States, and so on. About ATENA, as I told you, it is directed or is targeted for concrete, and one of the three unique features in ATENA is reinforcement modeling, visualization of cracks, and the possibility to have a runtime visualization. This is what you see on the bottom left part of this slide. So as the analysis is running, we will come to that later. You can see how the structure deforms, how the crack propagates, and so on. This gives an overview of our international activities where ATENA is being used. So currently we have about 600 companies using ATENA and more than 2,000 users. Let me just very quickly summarize one of the main features of ATENA for modeling concrete. So we are, as I told you, we are focusing on reinforced concrete structures. So this means we need to have a good model for concrete. For that, we are using this kind of three-dimensional criterion, as you can see on the left picture. It is based on the Menetre-Villam three-parameter model criterion. And to model cracks, we are using fracture mechanics-based approach. So the release of energy across the crack surfaces is based on fracture mechanics using the fracture energy material parameter. And we are using the so-called crack bend model to consider mesh objective results. Okay, so this model combines cracking model by using Rankine type of criterion, softening law, which takes into account the fracture energy, and the energy dissipation is controlled by the crack bend model, which takes into consideration the size of the finite element where the crack occurs. For concrete, we are using plasticity-based, or for concrete in compression, we are using plasticity-based formulation, where the evolution of this three-parameter criterion I mentioned previously is controlled by has two phases: hardening phase as well as softening phase. Sorry, there is some microphone turned on, so I have to turn it off. Okay. So this evolution of this criterion, concrete criterion, has two phases: hardening and then softening. Again, the softening part is controlled by an approach similar to the crack bend approach in tension. We call it crash bend in compression, where again the dissipation of energy is controlled by the size of the finite element. Well, how this works, the best way how to check this, whether our models are, let's say, representative and accurate, we participate in various round-robin competitions, which is the best test. Those are the competitions organized very often by various professors, where before making a test, they send out the geometry and we perform the calculation. So this summarizes some of our recent successes in various competitions. Most interesting one may be this one from Toronto, where a very large beam, 90-meter span, 4-meter height, have been tested, failing in shear. And here I can show you just we have some animation also here, how the crack pattern was predicted in ATENA. This shows the crack pattern, or the top figure shows the crack pattern from the experiment. And we had quite a good success in predicting the peak load. This beam actually consisted of two tests. First, they tested this right side, where there was no shear reinforcement, and then they continued the test to break the left side where there were shear stirrups. So two results were obtained for this beam. These circles indicate our results. So in one case, we slightly over-predicted. In the other case, we slightly under-predicted. But we remained in this so-called yellow zone, which was the zone of 10% accuracy. And these tables show the scatter of results. So you can see it was not so easy to predict this behavior. And we have to admit to be in 10% is, let's say, a little bit of luck, because we know from some papers and some studies that the accuracy of predicting general accuracy is about 16 to 20%. But anyway, we were very happy with this result. So let me now continue a little bit to summarize the main features in the new ATENA. So one interesting features in the latest ATENA is the modeling of fiber-reinforced concrete. For fiber-reinforced concrete, what we often have to do is to determine a suitable softening law, which depends on the fiber types, fiber volume. And typically, this is the only thing that is known is the results from this kind of 3-point or 4-point bending test. So first stage of such an analysis in fiber-reinforced concrete is to make an inverse analysis of these beams to determine the suitable stress-strain diagram. And then after fitting this stress-strain diagram, it is possible to apply it to some real-scale structures. And for that, we have, first of all, there is a tutorial in ATENA documentation how to do that. But we are now, we will be now releasing soon this tool, which can do this automatically. So this is the snapshot of these two running. The yellow line is, yellow curve is the measured response. The blue one is, let's say, the initial guess from the initial estimation of the parameters. And then the program automatically fits the best results, as you can see from this snapshot from the program screen. And then this is an example of such an application in the modeling of TBM tunnel lining in Czech Republic. The other new features in ATENA is the possibility to model also beam structures or shell structures, which we are continuously improving. And this slide summarizes all the ways how, let's say, we can model a beam. Of course, the top one approach is to model a beam as a 3D, using 3D solid elements. Then, of course, we can model it as a 2D structure using 2D solid elements. And of course, then we have the same using quadratic elements. But it is also possible in ATENA to model this situation using shell elements. And we have two types of shell elements, 3D shell element, which looks like a 3D beam, a 3D solid element, but internally it is actually formulated as a shell element. And of course, classical situation or classical type of such an element is 2D shell element, which you typically see in other programs. The advantage of this 3D shell element is that you can easily combine it with solid elements, so that you can create a combined model. And the same situation or same possibilities we have also for modeling beams. So there is, of course, the standard 1D beam element, which is modeled as a linear element, but also there is a 3D variant of this element, which again, the main advantage of this element is that it can be easily combined with solid elements. As is shown on this next slide, how you can, for instance, use this combination of elements in some kind of frame, column slab structure. So you can use the solid elements around the columns to simulate the shear failure that may occur around the columns. And for the areas where we have bending behavior, we can use shell elements for the plate and beam elements for the columns. And of course, also the classical way of modeling can be also done just using 2D and 1D element. Just to summarize, this has been already available in previous versions of ATENA, and I just would like to highlight it again. It's again further improved in this new version, that you can make cuts through the structure, generate these cuts along the whole structure length, or in this case, the beam, and evaluate the classical engineering quantities like moments, shear forces, or normal forces. There is a question from Asdam. When using 3D shell elements, whether it is possible to see the stress strain across the depth. Yes, of course, it is possible. It can be either displayed as a contour areas over the element surfaces, or there is also possible to have a cut. Define a cut and have these strains or stresses across the cut. All right, yeah, here is this internal forces plot for more complicated structure, which combines again these various elements into a model of a bridge structure, which has some cables. And also nowadays, and also the new version 5.7 has been very much improved in the speed of processing and post-processing of large-scale structures, like you can see on this high-rise building model, which was modeled with ATENA using solid elements, shell elements, and you can see here the various modeling of the slabs and of the external diagram. This has been already in the previous versions, but in ATENA you can also display the make an eigen analysis to calculate the eigen modes, eigen frequencies, in this case of this high-rise building. Okay, now I would like to continue or focus on the main topic of the presentation today. This is about the durability modeling. So how we can use that in the latest ATENA version. So as you know, the durability is a very critical issue nowadays because the infrastructures in most countries are aging. So the corrosion and other durability issues may be a big problem. So we can divide the phase of structural degradation caused by corrosion into these 4 phases. First, there is a so-called initiation phase. That is time it takes for the various chlorides or other ions to propagate to the reinforcement. Once they reach the reinforcement with some critical concentration, a so-called propagation phase starts, which again can be divided into three phases. First phase is the phase before the cover cracks. Then as the further the expansion due to corrosion continues, it causes a spalling of concrete cover, which again increases the rate of corrosion. And at some point, we may observe collapse of the structure. So this can be simulated with ATENA. And this slide summarizes the approach we are using. Basically, we have introduced a new surface condition which can be applied to our structure. So in this case, if we look at this simple structure, at the bottom we can apply to the bottom surface, we apply some chloride concentration, which simulates the environmental situation or condition on that surface. And as then we are using one-dimensional models to simulate the propagation of ions to the reinforcement. Because in ATENA we can have a discrete model of the reinforcement. We know what is the distance of this reinforcement at each point from this loaded surface, or from this surface with the chloride concentrations. And we can determine using these models, which are available in the literature, this induction phase. So when the critical chloride concentration occurs at the depth of the reinforcement. And then once this starts, when this propagation phase starts, we can model the corrosion of the reinforcement considering the chloride concentration which is available. And this is then shown here. As you see, reinforcement starts to corrode. These models also can take into account the presence of cracks. So if there are some cracks located at that location, they of course can speed up the process of ions or chlorides propagation. So now let me show some practical application. One example in Germany, where we applied this model to simulate the durability, structural health of this bridge. Well, in this particular case, it was also combined with monitoring. So some monitoring strain gauges or some monitoring system was introduced on the bridge. And the main idea was to use this monitoring to first of all determine the distribution of the loads or traffic on the bridge. And in addition, it allowed us to calibrate our model, to verify that our model is representative. So in order to do that, of course, this measurement had to be calibrated. These are pictures from another bridge, but same approach was used in that German bridge. So first, this monitoring system was calibrated by some tracks with predefined weight. And there was a sensor, also laser sensor, counting the vehicles passing. And this can then show you the process of this calibration. We then were passing, the tracks which were measured. And the advantage of this is that this system was introduced there for a longer time. And it recorded the weight of the various vehicles, and then we could use this calibration using the real traffic of the bridge. And then, after the model was calibrated, we could simulate also or make some live predictions. So we could apply. We could consider or assume some chloride concentrations depending on, for the various surfaces, the various chloride concentration was used because of course the top surface is the most critical one where there is the highest concentration of chlorides. And this shows then the corrosion. Such a picture you can obtain now in ATENA, which can show after 100 years what will be the amount of corrosion. So in this critical situation, of course, by many years, you see some of the reinforcement is almost gone. And this, of course, influences very much the failure of the bridge. And we can then perform this kind of analysis. That's what I will show you in the next part of today's presentation. That we can have, of course, we can evaluate the strength of the bridge before any deterioration, which is this blue curve. And then as we go in time, we can always check the structural strength or load carrying capacity after 50 years, 100 years, or 150 years. And we can always compare that to the expected load levels, dead load, live load, or the design load level, the ULS. And then we can plot this, let's say this is kind of a reliability of the structure, how it evolves in time. And here you can see that we also considered some characteristics, some statistical properties of the bridge. So if you assume average or mean properties of the bridge, if you assume characteristic properties of the bridge, that is the green line, and the design strength of the bridge, considering some safety formats, and this will give us, let's say, 100 years of the life expectancy. So, okay, so this is just the summary which was used in this particular situation. First, the numerical model was calibrated using the cooperation with the bridge monitoring system, and then we could use this calibrated model and this new durability model of ATENA to make some life cycle or life structural health predictions in the future. So, okay, there are some questions, so let me answer them. From Giuseppe, he asked about how did you choose the sulfate chloride concentrations? Of course, this is a big problem. In some projects, which I have not shown here, but in some projects, which is the best way, you can check that by taking course. You can take course from the bridge, which you investigate, and from that you can you know what is the chloride concentration. But in other cases, like in this case, we considered some typical chloride concentrations which can be expected from situations which are reported in the literature.
This would be enough.
Okay, there's another question. Is uniform corrosion assumed, or do you use assumptions for the pit distribution? Yes, of course, I will come to that later. When you apply this surface condition or this chloride concentration condition, you can select. This is one of the parameters that you have to define as a user, whether you can expect uniform corrosion or pitting corrosion. So in this case, because we expect that this chloride concentration will start at certain locations, so we assumed pitting corrosion. All right, so there are no more questions at this point. So I will continue and show you the application of this process on a practical example. Let me close this. And close the presentation. And now I'm showing ATENA preprocessor, which is the program GID. For those of you who are not familiar with ATENA, I want to make a brief introduction here. We have currently two types of products. One we call engineering, which is good for smaller analysis and supports only static analysis. And then we have this more advanced version, which we call ATENA Science, which supports dynamic, static, transport, and creep analysis. And for that, for this version, we are using program GID, which comes from University of Barcelona. And this is our preprocessor. And this is how the preprocessor looks like. Let me make just a brief introduction how you prepare the model. So typically, you define the model by defining points, connecting them to lines, then forming surfaces. Surfaces in GID are indicated by these pink lines. And then you form the surfaces to create a volume, which is indicated by these bluish lines. Of course, it supports possibilities for extrusion, copying, also some Boolean operations on the 3D volumes that are created in this way. For that, we provide some tutorials. So if you install ATENA and go to the documentation, there you will find various tutorials which will give you an introduction to modeling in GID. So in this particular situation, it is this kind of beam. It actually corresponds to a problem which is reported in one of our papers. And it is a part of a bridge, which is part of a beam, which is taken from a real bridge in Japan. So we are, because it corresponds also to this beam was tested in the laboratory, so it is assembled in a, or the model is prepared as a laboratory specimen. So we have some loading plates, supporting plates where we then apply the loads. And then there is reinforcement. So you can see this is using the discrete model of reinforcement in ATENA, where each reinforcement can be introduced into the model, which is particularly useful for this durability modeling so that we can calculate the corrosion for each reinforcement. All right, so let me, in this durability modeling, first of all, we need to always think about the loading scenario. This is actually important for any analysis in ATENA. We always have to, because we are performing a nonlinear analysis, to check the structural capacity or structural behavior. So we always have to think about what kind of scenario we want to use. So in this case, we have the following scenario to simulate something which is close to reality. So the scenarios or the loading history is defined in ATENA by this interval data. Each interval represents a certain type of load. It is possible to change the loading, change the supports from one interval to another one. So we first have one interval where we apply the self-weight. Then there is second interval where we applied some load. This can, for instance, represent service load. And this load will be then acting on the structure while this corrosion process will be activated or will be simulated. So we first apply self-weight, then some service loads, and then we have a third interval where we will apply this chloride condition. So we can display that, how it is done in this situation, by checking the applied loads. This is done by this condition dialog, where it will be applied on the surfaces. So we have to select this surface icon, and this gives us a list of possible conditions in ATENA. And the conditions we want to use now is the chlorides for surface. You will notice that the same type of condition is available also for carbonation. But in this example, we assume a chloride attack. So we have this chloride condition. And we can see that in this particular situation, we are applying 3 types of chloride conditions on these surfaces. So let's very briefly go through these parameters. For that, I'm going to show another presentation which gives you a better idea what kind of parameters are necessary. So this is the dialog I was showing you. Let's quickly go through these parameters. So first parameter is this diffusion coefficient, which can be determined either from some tests from your concrete, but if it is not available, it is possible to estimate them from some tables available in ATENA theory manuals. So we have in ATENA theory manuals, there are some typical diffusion ratios for different concrete types, considering different water to binder ratio. This always is these coefficients or these functions or this diffusion coefficient always is derived for a certain time. It is possible to define this time there. Then important is this M coefficient, which again can be taken from these tables, either from the literature or from the tables available in ATENA theory. Again, this M coefficient is representative for a certain time, so this can be provided here. Important parameter is this CS, this is the chloride concentration. This is, of course, a problem on how to determine it, but there are certain values available for typical situations like a splash zone or surfaces which are regularly treated by some de-icing solutions. Then we need to define the critical chloride concentration, which starts the corrosion. This again, this depends, of course, on there are various values available in the literature, so it is of course necessary to make some decisions there. And okay, the next is the concrete cover. Well, here I want to differentiate because here you can define the concrete cover, but of course it is clear from our model that we have different cover depths for different reinforcement. So so this may be a little bit confusing, but how the program works, that in general, it will determine the concentration of the chlorides for this depth that you provide here. This is one output you will obtain as a kind of a contour areas during the analysis. This will give you an information about the chloride concentration at this given depth, and it will also tell you what is the initiation time for this depth provided here. But so this is one information the program provides, and the other information is that it will be checking each individual reinforcing bar, which of course has a different depth, and it will be checking this reinforcement bar to find out when the critical chloride concentration reaches the reinforcement, and then it will start the corrosion process for each reinforcement or for each point along each reinforcement. Another parameter is this maximum reinforcement depth. This is again the parameter which is used by this reinforcement model, because some reinforcement is very far away from this surface where we apply this chloride condition. So it makes no sense to check these reinforcements which will never be affected. So you have to provide here certain depth which the program uses. So any reinforcement within this depth within this distance from this surface will be considered in this durability model of the corrosion. Splitting strength has to be provided. This is to determine cracking of concrete cover and the spalling. The next parameter is the corrosion rate after the spalling occurs, because after the spalling occurs, the corrosion is then controlled by the external environment, and for that the program uses these kind of definitions, or can be used, or the value can be taken from these tables. This is the parameter which controls the type of corrosion. That was the question somebody asked before. So this is now up to the user to determine whether we expect uniform type of corrosion or pitting corrosion. So typically for chloride corrosion, we recommend to use 3 as a pitting corrosion. For uniform corrosion, which for instance occurs for carbonation, R can be 1. Now important parameter is this third one, where we define the function, the time function. Because right now I'm using this chloride or this durability model in a static analysis. In the static analysis, we don't have a time, there is no time. So you have to define some additional function where we can say that from step 30 to 50, which corresponds to this interval where we want to apply the chlorides, we have to say that step 30 means time 0, and step 50 means, in this case, 60 years. Units are days. This is up to the user to select the units, but if we select days, then 60 years corresponds to 21,900 days. And the other parameter important is the cement mass. This is because this CS, which is shown here at the top, the chloride concentration is given per mass of binder. We need to provide binder mass to the program as well. And temperature offset, this again, this temperature offset can be either obtained from thermal analysis, but in this case we are not making thermal analysis, so we need to tell the program what is the typical temperature, which then affects the speed of corrosion. So these are the parameters that we need to provide. As you can see, to determine some of them may be sometimes tricky. Right now it is very general, so user has a quite extensive possibilities to modify this. On the other hand, it gives some demand on him to find out the suitable parameters. We are working on improving this to have some kind of wizards to simplify this definition. But in current version of the program, 5.7, it is like this. To help you to define the individual parameters, it is possible to look into the theory manual. Okay, so let me go back to our model. So we applied these boundary conditions simulating the chlorides, and we are applying in the third interval. And we know here from the definition of our interval data, we know that first interval is 10 steps, second interval is 20 steps. So we know that the third interval is from 30 to 50 steps. And then that's why we need to define this time function, which relates the step to some time. And then we have a third interval, or fourth interval, I'm sorry, interval number 4, where we make an overload. So we then load the structure up to failure. And in this way, we can determine what will be the strength of the structure after 60 years of chloride attack. And if we want to do it in various years, so we always modify the analysis, modifying the time function, and we can then make a kind of a study, seeing the effect of the chlorides at various times. So we can run the problem now. So I will start the analysis for this particular situation. So it is starting the program. Basically now from GID, it is generating the input file, and it will automatically then start the ATENA program. And as I told you, one of the unique features of ATENA is that as the program is running, you can already observe what is happening. So this is now out. This program, which has been started now, is called ATENA Studio. So this is the main program which allows you to observe the process of the analysis. And it is also a program which can be used as a post-processor. But as I will show you now, you actually have a full post-processing capabilities even as the analysis is running. So this is nothing new for the current users of ATENA, but because some of the participants have not used ATENA before, so let me allow you to spend some time on this. So we see, let me first show you the input file, yes? So we can explore this input file. So this is basically a textual file which has been generated from this GID model. And of course, if somebody is an expert, you can always go and modify this input file by hand. And now we can explore. Now we can see in the various windows what is going on. So this is the shape of this is the model, structural model. I will modify my screen a little bit so that you see the whole screen, because it is, I think it is partly covered for you by some of the windows on my screen. So here we can, for instance, display the deform shape of our structure, how it deforms. We can select the view, how we want to look at it. I like to have this solid view with the outline, and we can display the cracks. So we see now how the structure starts to cracking. But right now we are still, let's say, in this initial stage. We are applying the self-weight, and also we are applying some service loads. This structure is quite large span, so that's why there are already some, and it's not pre-stressed, so that's why we can see some cracks already from these load levels. What is very important is this graph window on the left. Right now, by default, it is showing the iterative process. So at first, the iteration was very quick. But once we start to see some cracking, we can see that the iteration is, let's say, more, or takes more time, and more iterations are necessary. And the iteration process we can follow at this window at the bottom, where we can see how the various criteria are converging. But very useful feature in ATENA is to define some monitoring points. I forgot to show them in the preprocessor, but in the preprocessor, we can define various monitoring points. Typically, we want to monitor the displacement of our structure. We can put some scalars. So I want the displacement to be in millimeters. And then we have defined some monitors which monitor the applied load. So for instance, we can follow the reaction, which will give us the total load acting on the structure, and it is normally in meganewtons, so I multiply it by 1,000 kilonewtons. So now this is a very useful, and I always recommend that everybody has a monitor in his structure, because you can then easily follow how the structure behaves. We see that initially it was linear, and once the cracking starts, the response, the stiffness has reduced, and we nicely see the kind of the response of our structure, which is now highly nonlinear. Okay, let me, so that it will take some time, let me run it on the background. And I have already finished the analysis here, so let me show the results. So this is the situation. Right now we are in our analysis somewhere here, but for the sake of time, it will take maybe, I don't know, 20 minutes to complete the analysis, but let's jump directly to the results. So what we see here, let me show the other one. This is for 30 years. And if I go back to the one which is probably more interesting to us, this is after 60 years. This is exactly the analysis which is running now. So, let's discuss a little bit what we see on this load displacement curve first. So we are applying the load, the service load. First it was linear, then we observed some cracking, so the stiffness changed, and we reached the service load. At this point, step 30, it is end of this service load scenario. We are applying, and then we are applying the chlorides. I told you that from step 30 to 50, we are applying the chloride. At this level, we keep the load constant. So that's why we see this plateau. But of course, due to the chlorides, which cause corrosion and reduce the reinforcement area, as you see here, this picture basically shows the relative reduction of the reinforcement cross-section. So we see some of these stirrups are almost gone. And the reduction of the reinforcement, of course, is causing the increase of displacement. So that's why we have this plateau. And then we make this kind of a virtual load test to determine how this reinforcement corrosion affects our load carrying capacity. So we perform kind of a load test of the structure. And we see that the failure load is at about 700 kilonewtons. I have already prepared the results here. So here you see what is actually the result from this analysis. The blue or the black line represents the initial structure without any corrosion. This red line is after 30 years, and blue line is after 60 years. So this is the summary and what this new feature of ATENA can provide you. So let me go back to the chat window and to see to try to answer some of your questions. So let me go back. So there is a question from Matthias. Can you define the model via scripting? Well, it is possible because this GID program has embedded scripting language, which is a TCL language. So this language could be used. But to tell the truth, we don't have so much experiences with that. So we are not using that very much. But we are working in that direction very much because we know this is a current evolution or the trend in all the simulation software to allow scripting. So already now, scripting is available either through GID with the TCL or ATENA. This ATENA input file also allows to use scripting. It supports a Python language. So there are quite a lot of possibilities for scripting even now, but we are working more in that direction as well. There is Matteo is saying fantastic. Okay, great. I'm happy that you like it. Francesco is asking, hello from Italy. ATENA user full. Yes, hello also. Giuseppe, if I apply different corrosion times to the same structure, should I get different induction times? Well, I don't think so. Then I'm not sure I understand this question, but the induction time should be always the same. Of course, if you introduce or if you apply different chloride concentration, then you will obtain different induction times. It should not depend on the corrosion times. But I'm not sure I understand the question. Matteo is saying, would it be possible to review the lesson on the ATENA website? Well, as I told you, we will provide you this recording. And yes, we are preparing also some tutorials and some video tutorials for this problem. Once they are available, they will be announced on our website and also on our social networks on Facebook and LinkedIn, which are devoted to ATENA. Mohammed is asking how to introduce shrinkage in ATENA 5.7. Well, there are two ways how to introduce shrinkage, either directly by defining initial strain. If I switch quickly back to GID, here under the conditions that you can apply, you can see that the one condition that you can apply to a volume, which means region, is initial strain. So you can directly apply shrinkage there as an initial strain. The other alternative is to use the creep model and apply some creep model. ATENA supports various creep models. Most often we use the Bajan's B3 model, but there is also a FIB model, or Eurocode model. And then the shrinkage is considered according to that particular model. So the answer is yes, it is possible to apply shrinkage. Edward Bennett is asking, I have a 90-year-old bridge. We know the spans, secondary beam and depth of concrete, some idea of reinforcement. I guess with this new version, I could predict the remaining life in the concrete, knowing how all steel beams are corroding as well. Yes, yes. However, I want to say that the current corrosion model is only for reinforcement. We don't have any corrosion model for steel beams. So you could do that, but you would have to consider the reduction of steel in the steel elements directly by reducing Young's modulus or the area or strength of the steel beams, let's say manually. Seat is asking for reinforcement. Do you keep the real distance, i.e. for stirrups or tie around the long bar? Do you use half of each? I'm not sure I understand it, but you can see that clearly from our results that we indeed consider the distance of each reinforcement. Even in this in these stirrups, we consider the fact that the chlorides propagate from two sides. So you can see these stirrups at these bends are more corroded than the longitudinal reinforcement. Mohammed is saying, in the output of the B model, some cracks are wider than others. How to measure crack width? Well, in ATENA, of course, this is one of the important outcomes. I can show it here. You can always display or show the crack width. So program gives you an information about the crack width, and the crack width is calculated from this crack band model. That means we basically take the fracturing strains inside each finite element, and we multiply it by the size of the element, and in this way we estimate the crack width. So, and then I told you that this this chloride propagation model takes into account the presence of these mechanical cracks. So the chloride propagation is faster at the location of the cracks. If I go to this step 50, which is the step at the end of the, I have to switch to post-processor, where I can go to various steps. And I can go to step 50. Well, in this particular situation, yeah, the effect of the crack width is not so pronounced because you really need to have a very wide cracks. If the cracks are, let's say, below 0.1 millimeters, the effect on the chloride propagation is not very big. This is also why the codes require you to have crack widths smaller than 0.3. But once you have larger cracks, then there is a significant effect on the chloride propagation. Okay, Frances. Oh, when the newest version 5.7 will be available for download is another question. Actually, it is available now, but you have to send us a request. But I expect that before the end of this month, we will release it as a public version. But if somebody is interested even now, please send us an email and we will send you the link to download and test this version. Column Francesco says, column subject to compression with the action of chlorides, is it possible to capture the instability of reinforcing bars? Well, it is. However, currently the bars or the reinforcement is modeled by truss elements, which do not have any bending stiffness. This is the typical or the default model in ATENA. But nowadays, the new version 5.7 also allows to model the reinforcement using these beam elements. And then you can consider also the bending and instability. But even with the truss elements, you can capture the instability. But of course, maybe the bending stiffness of this reinforcement will be slightly underestimated. Otherwise, ATENA always considers the geometric nonlinearity. This is always on because ATENA always updates at each step. At the end of each steps, the coordinates are always updated. So this means the equilibrium is always checked in the deformed configuration. So any buckling effects are automatically considered. Mohammed, you have chloride diffusion. Do you have moisture diffusion and shrinkage? Yes, this is the transport model. In the ATENA transport model, you can simulate the transport of temperature and also moisture. Syed is asking, what solver do you use? When I use Itsuzuka instead of Pardiso, the result change. This is run with Pardiso. Of course, this should not change unless maybe the solution is not fully converged. If it is not fully converged, then of course any slight discrepancy due to the various solvers may result in different results. Another question is it possible to view results regarding the spalling phase? Well, this is not currently available fully in ATENA. I will have to check on that. Yeah, the ATENA doesn't tell right now, if we look at these corrosion results, whether we are in the which propagation phase we are, whether we are before the cracking, after the cracking, before the spalling, and after the spalling. There is no information on that currently. It's a good idea. We will think about it to introduce this in the future because it is an interesting result, of course, interesting information, and it is, of course, available inside the program. I just want to give you an understanding that, of course, this approach considers these effects. Right now, we are not simulating this exactly. By that I mean we do not, as the reinforcement corrodes, of course it expands, and this expansion should introduce some initial strains in the model, and this we do not consider. We consider it, let's say, indirectly, because the approach we are considering or thinking about is the fact that for engineers, it's not so important that we lost some concrete. What is more important is the fact that once spalling starts, the corrosion rate changes. And because we know the distance of the reinforcement from the concrete, we know from the surface, using the current empirical model available in the literature, we can estimate when the cracking starts, when the spalling starts, and based on that, we can increase or change the rate of corrosion. So our model is, let's say, kind of engineering, and to capture really the falling of or spalling of concrete, very fine models would be necessary, which would drive all this analysis to be very complicated. So this is just to give some information about that so that we don't have some misunderstanding. Matteo, does the model take into account the reduction of adhesion? Not yet, not yet. Yes, this is an important question. You're right. Currently, the model does not reduce the bond. And of course, in ATENA, we can have a bond model. So this is our next stage of development, to also reduce the bond behavior. Another question, does chloride attack modeling in ATENA assume deletion of concrete elements? I think I told you, answered that already. No, not yet. The philosophy we are considering is that it is not so important for the structural behavior that some part of the reinforcement in the tangent region is lost. What we are considering to be more important is the fact that the corrosion rate has changed. We are considering that by changing the corrosion rate, but we do not delete or we do not remove any concrete elements. Is it possible to use the deletion of concrete elements that failed due to failure? Right now, it is not fully possible. It is somehow possible because there is this possibility when you define, if I go back to GID, and if you define the concrete properties, there is an option now in the new version of ATENA that you can say that you can inactivate some elements which have negative Jacobian, or some elements which have large error, or which are very distorted. And this is typically the situation of elements which are fully damaged. So with this option, it is possible to inactivate them. But we are working in that direction as well, but because to delete elements which are reaching some damage threshold. On the other hand, it is a little bit risky, because if you remove those elements, then you may end up with some indefinite stiffness matrix. So it is a little bit difficult. So, okay, I think we are reaching our time. I see some people are thanking or appreciating the presentation. So thank you very much for those words. And I also thank you very much for participating. And please, if you have some questions, do not hesitate to contact us. And I think we will stay in touch. And our idea is to organize these webinars more often, especially nowadays when it is difficult to meet in person at some conferences or exhibitions. So we plan to be more active with these webinars. So thank you again, and hope to see you again in some future webinars, or maybe at some conference also. So I'm stopping the recording now, and as I told you, we will send you the recording by email, hopefully tomorrow or before the end of this week.